Hi guys, I welcome you to my YouTube channel. This is IBM. Do not forget to download the videos. You can share the videos, like the videos, write a comment on the videos. Do not forget we are dealing with solved past paper questions. This is going to be AS. This is AS Physics. These are multiple choice questions of Physics 9702. That is mostly paper 1. It is always 1, 1, 1, 2, or 1, 3. Remember we are dealing with kinematics and dynamics, and this is going to be part 10. I think we stopped on part 9 the previous weekend. So without wasting time, I would like to take you to the document so that we start solving the questions. In part 9, we stopped on page 84. So in page 85, that's where we start from. We shall start part 10 from page 85. Okay, so I will start with this question. A light ball falls. A light ball is falling vertically through air. It is falling through air, so air resistance cannot be neglected. The variation with time of the resistive force Fr acting on the ball is shown. At which times are the speed of the ball 0 and the speed at a maximum and the speed at a maximum and the acceleration 0? So I want you to recall from your concepts of dynamics that the resistive force is always directly proportional to the square of the speed. So it means when Fr is constant, when the resistive force is constant, when the resistive force is constant, it means that the speed is constant. So it means because Fr is directly proportional to the square of the speed, so if Fr is constant, it means the speed is constant. So it means V is also constant. So from the graph, when the resistive force is constant, means the speed is also constant. And if the speed is constant, it means the acceleration is 0. So when the speed is constant, it means the acceleration is actually going to be 0. So this is basically at acceleration. So here when the resistive force, not the resultant force, but the resistive force. Of course, you know, people may think acceleration cannot be constant when the force is constant. Acceleration cannot be 0 when the force is 0, but this is resistive force. When the resistive force is constant, it means the velocity is constant because the resistive force is directly proportional to the square of the speed. And if the speed is constant, there is no change in the velocity, so the acceleration is going to be 0, and that is at t2. So the acceleration is 0 at t2. So we can begin by that. Acceleration is 0 at t2. So we eliminate this point where we have t1. So the acceleration is 0 at t2. And at t2 velocity, because at t2 speed is constant, so the acceleration is 0. So that is going to be terminal velocity. Then at t1, of course, at t1 the force is the resistive force is 0. We see that from the graph. At t1, the resistive force is equal to 0. And if the resistive force is 0, even V is 0 initially. So V is also equal to 0 initially, because remember, V is resistive force is directly proportional to V. So at t1 where the resistive force is 0, it means V is also equal to 0 initially. So 0 speed is at t1, not at t2. So 0 speed is at t1, not at t2. So this will eliminate D because it is showing that 0 speed is at t2. It is supposed to be at t1, so our answer is going to be B. So at t2 the speed is maximum, the acceleration is 0. At t1 the speed is 0, so the answer is going to be B. A sphere is released and falls. Its initial acceleration reduces until it eventually begins to travel at constant terminal velocity. Which displacement time graph best represents the motion of the sphere at constant terminal velocity? Remember, the gradient of a displacement time graph is the velocity. So the gradient is the velocity. The gradient is going to be the velocity. So it is the sphere is released, so it means its initial velocity is going to be 0. Its initial acceleration reduces until it eventually begins to travel at constant terminal velocity. Because it is released, initial velocity is 0, it means the initial gradient should be 0. So it means A is out because the initial gradient is not 0 for A. And C is also going to be out because initial gradient is not 0. Here it is showing initial velocity is not 0 because the initial gradient is not 0. Even here, the initial gradient is not 0, so initial velocity is not 0. Similarly, even, of course, for D, the initial gradient could be 0 because it is a curve which is almost horizontal. And for B, the initial gradient is 0 because it is a curve, it is almost a horizontal line. So we have to choose between B and D. But because because of acceleration, the gradient must be the gradient increases because of the acceleration. Its initial acceleration reduces until it eventually begins to travel at a constant terminal velocity. So it means at terminal velocity, the acceleration should be 0. So the acceleration starts decreasing, acceleration decreases to 0. If acceleration decreases to 0, it means velocity becomes constant. So the velocity becomes constant. So V tends to a constant value. Because the acceleration reduces, so V tends to a constant value. That means at terminal velocity, the gradient must be constant. At terminal velocity, I'll quote Vt, the gradient is constant. So how do we show that the acceleration, how do we show terminal velocity? The gradient must be constant. B is going to be out here because the gradient is increasing. You see the curve is becoming more vertical, so here the gradient is increasing. Yet D is going to be correct because, first of all, here we see that the gradient increases. Here the gradient increases, which means the velocity increases. There is an acceleration. But then here we see that the velocity becomes constant. The gradient is now, here V is constant because it's a straight line. So when V is constant, it means the acceleration is equal to 0. So at terminal velocity, the gradient must be constant, so it must be a straight line at terminal velocity. And when it is a straight line, the velocity is constant, the acceleration is 0. So since the acceleration reduces, then we must reach a constant velocity, we must reach a straight line. So the answer is going to be D. An insect jumps with an initial vertical velocity 1 meter per second, reaching a maximum height of 3.5 times 10 power minus 2 meters. Assume the deceleration is uniform. If the deceleration is uniform, then equations of motion can be used here. So I will use v squared equals to u squared plus 2as. If it is undergoing a deceleration, then it means the final velocity is going to be 0. So I'll say 0 squared is going to be equal to initial velocity is 1 squared minus, because it is a deceleration, the acceleration is going to be negative. So this will be minus 2 times the deceleration, which I don't know, times the displacement it moves, which is 3.5 times 10 power minus 2. So I'll check the answer here by just pressing my calculator. On the left hand side, I have 1 squared divided by 2 times 3.5 exponent minus 2. So this is giving me a 14.29 or 14.3 or 14. So acceleration is equal to 14 meters per second. So the answer is C. A body having uniform acceleration A increases its velocity from u to v in a time t. Which expression would not give a correct value for the body's displacement during time t? So if it is uniform acceleration, then the equations of motion can apply. For example, we know the three equations of motion, such as S equals to a half into u plus v times t. That equation is a general equation which we can derive the third and the second and the third equation. So s equals to, since it is uniform acceleration, then it is going to be a straight line. So it means the average velocity is a half into u plus v divided by 2. Then times time, that is the average velocity times time. So v plus, we don't have this equation here. So the other one could be s equals to ut plus a half at squared. That equation can give displacement. And then I think we have it here. The other one could be v squared equals to u squared plus 2as, which implies if I make s the subject, s is going to be v squared minus u squared divided by 2a. S is v squared minus u squared divided by 2a, and this is a difference of two squares, so it can be v minus u into v plus u divided by 2a. So we have that equation here, so this one will also give us displacement. And also, a body having uniform velocity, uniform acceleration, a increases its velocity from u to v in time t, which expression would not give a correct value for the body's displacement during time t. So first of all, this one here will not give, I think the answer is going to be D. D will not give the displacement because v minus u over 2 is not the average velocity, so the answer is going to be D. Now, somebody may ask, why not Vt minus half at squared? So this equation here is the same as ut plus a half at squared if the acceleration is negative, and if u is the same as, if u was v, or if u and v have been interchanged, then this will be vt minus a half at squared. So this could also give us a correct value for the displacement. So the answer is going to be D. A molecule of mass m traveling at speed v hits a wall in a direction perpendicular to the wall. The collision is elastic. What are the changes in the momentum and kinetic energy of the molecule caused by the collision? So if the collision is elastic for the molecule, the kinetic energy with which it hits the wall should be the kinetic energy with which it leaves. So the change is going to be 0. So 1, for the molecule, the kinetic energy should be conserved. So it means the change in kinetic energy must be 0 for an elastic collision. So we ignore B, because B is saying the change in kinetic energy is mv squared. So it should be 0. Then for the molecule alone, if it is just the molecule alone, it should be having a change in momentum. There should be a change in momentum if the molecule collides with the wall with the initial momentum mv. Then if it rebounds, its momentum will be mv in the opposite direction. Then the change in momentum for this molecule alone, the change in momentum is going to be mv minus negative mv, which is equal to twice mv. So it means our answer is going to be C. For the molecule alone, the change in momentum is that. But if we consider the molecule and the wall, total change in momentum would be 0. But considering the molecule alone, its change in momentum is going to be twice mv. A child on a sledge slides down a hill with acceleration a. The hill makes an angle theta with the horizontal. Total mass of the child and the sledge is m. The acceleration of free fall is g. What is the friction force F? So the child is having an acceleration a down the slope. So I'm going to resolve the weight. Let the weight of the child be m times g, because the child has mass m. When I resolve the weight vertical parallel to the plane, it will be mg sine of theta. Since there is an acceleration down the plane, it means the resultant force, which is given by ma, should be equal to the force down the plane, which is mg sine theta minus f. So it means if I make f the subject, f is going to be equal to mg sine theta minus ma. If I make f the subject, remember f is the resistive force or the friction force. So it means f is equal to m into g sine theta minus a. So the answer here is going to be automatically C, m into g sine theta minus a. So the answer is C. A box of mass 80 kilograms rests on a horizontal rough surface. A string attached to the box passes over a smooth pulley and supports a 2.0 kilogram mass at its other end. When the box is released, a frictional force of 6 newtons acts on it. What is the acceleration of the box? Okay. So first of all, there must be tension in this string here. Because it is the same string, then the tension here is the same as the tension there, but they're just in the opposite directions. So if there's an acceleration, then the box must be accelerating in that direction. Of course, the 2 kilogram mass must be accelerating downwards. Okay, so this one, the acceleration here is downwards. So there is frictional force between the box and the surface. So there's frictional force here. I will call it F, small letter F for frictional force, small letter F. Okay, when the box is released, a frictional force of 6 newtons, this is 6 newtons, acts on it. So considering the box and using Newton's second law, the resultant force M times A should be equal to the tension in the string minus the frictional force F. So the mass of the box is 8 times its acceleration A should be equal to the tension minus the frictional force F. Then if I consider the 2 kilogram mass, moving downwards, so the resultant force for the 2 kilogram mass is going to be using MA, resultant force equals MA, so the resultant force here is going to be 2 times its acceleration A is equal to the weight downwards is going to be 2 times G, which is 9.81. So since it is accelerating downwards, the weight downwards is bigger than tension, so this is going to be 2 times 9.81 minus the tension which is upwards. So we have this equation here and we have this one here. So I am going to simply add the two equations so that T disappears. So when I add the two equations, the frictional force was given as 6 newtons, so I'm adding the two equations. 8a plus 2a, which is 10a, is equal to T plus minus T disappears. So I remain with 20 times 9.81 plus negative f, that is minus 6, because this is the same as 8a equals to T minus 6. So I'm adding the two equations, so it will be 20 times 9.81 minus 6. So I'm trying to find f from my calculator. So I have 20 times, is it 20? It is 2. This is 2, not 20. So 2 times 9.81 minus 6 divide by 10. So I'm getting the acceleration as 1.36 or 1.4. So this is 1.4 meters per second squared. So the answer is going to be A. What is the definition of force on the body? Of course, we know force is the rate of change of momentum. So this, without wasting time, force is equal to the rate of change of momentum. So the answer is automatically C. A stone is thrown horizontally from the top of a cliff. Air resistance is negligible. If air resistance is negligible, it means the acceleration is going to be constant. The acceleration should be constant. Now, because this is a velocity time, and by the acceleration should be constant and should not be zero. It should be actually supposed to be about 9.81 meters per second squared, so it should not be zero. So if this is a velocity time graph, then the gradient is the acceleration. So gradient is equal to the acceleration for a velocity time graph. And remember, it should not be zero. So the gradient should not be zero. So A is wrong because A is showing that the acceleration is zero. B is also wrong because B is showing that the acceleration decreases. Here it is the gradient is decreasing, so the acceleration decreases. C is also wrong because C is showing that the acceleration increases because the gradient increases. And D is correct because it shows that the acceleration is constant because the gradient is constant. So the answer is going to be D. A sprinter runs a 100-meter race in a straight line. He accelerates from the starting block at a constant acceleration of 2.5 meters per second squared to reach his maximum speed of 10 meters per second. He maintains this speed until he crosses the finish line. Which time does it take the sprinter to run the race? Which time does it take for the sprinter to run the race? Okay, a simpler way of visualizing this could be maybe by sketching a simple graph, of velocity against time. So if I was to sketch a graph of velocity against time, I think this would be like this. He accelerates, so the velocity increases. He accelerates, the velocity increases. The acceleration is 2.5. He accelerates to reach his maximum speed of 10, so this is going to be at 10. He maintains the speed until he finishes, so he maintains the speed until he finishes. Which time does it take the sprinter to run the race? Okay, let's begin by finding the time it takes for the acceleration. So using V, I want the time here. If this is 0, using V equals to U plus AT. The velocity reaches is 10 if it starts from rest. So it means, of course, it's going to start from rest. So initial velocity is 0. So this will be times the acceleration, which is 2.5 times t. So the time here is going to be automatically 4. 10 divided by 2.5 is 4. So this time is 4. So the time here is, therefore, if the total time is t, so it means the time it takes here is going to be t minus 4. The time it takes when moving at a constant speed is going to be t minus 4. But remember, the displacement or total distance is the area under the graph. So I will say distance is equal to the area under that graph. Or I can add the distance it travels at a constant acceleration plus the distance it travels at a constant velocity. So area under the graph, for the first part, it is a half times, it is a triangle. For the first part is a triangle. This one here, a half times the time, the base is 4, times the height is 10. This is the distance it covers at a constant acceleration, plus for the rectangle, the height is going to be 10 times t minus 4. But remember, the total distance is 100, so this will simply be equal to 100. So I just solve for t, the time it takes for the rest of the race. So I will just check my calculator. Half times 4, that is 220. So we have 20 plus 10 t minus 40 equals to 100. What is t? 140, or that is 80 divided by 10, which is going to be 80. Okay, so that is 80, so that is 120, so that is 120 divided by 10, which means t is going to be 12 seconds. So t is, remember, t is the total time from 0 to, I put t here, t is the total time here, so t is going to be 12 seconds. So the total time there is 12 seconds, so the answer is going to be C. Okay. Alternatively, you could use, you could find the distance. You could find the distance traveled at a constant acceleration from s, from v squared equals to u squared plus 2as. So v squared is 10 squared equals to initial velocity 0. So this will be 2 times the acceleration, which is 2.5, times the distance s. So this means the distance s here is going to be 100 divided by 5. So this is 100 divided by 5, which is going to be equal to, I think that is 20 meters. That means the distance covered at a constant speed is going to be distance at constant speed is going to be therefore 100 minus 20, which is going to be 80 meters. Then you can now use, since distance is equal to speed times time, then the time here is going to be distance, which is 80 divided by the speed, which is 10. So the time for constant speed is going to be 8 seconds. So how about the time for uniform acceleration was 4 seconds. So the total time will be 4 seconds plus 8 seconds. 4 seconds plus 8 seconds, which will give you 12. Total time will be 8 plus 4, which still gives you 12 seconds. A firework rocket is fired vertically upwards. The fuel burns and produces a constant upwards force on the rocket. After 5 seconds, there is no fuel. After 5 seconds, there is no fuel. Air resistance is negligible. That means the acceleration is constant. What is the acceleration before and after 5 seconds? So if after 5 seconds there is no fuel, it means the resultant force becomes constant. So here, resultant force becomes constant if there is no more fuel. Resultant force becomes constant. So no more increase in, there will be no more increase in acceleration. No more increase in acceleration. There will be no more increase in acceleration, and if there's no more increase in acceleration, it means the acceleration becomes constant. So A is equal to a constant. A becomes constant. After 5 seconds, the acceleration becomes constant. So we ignore the ones which are saying 0. So we ignore B and D. Okay, but then before 5 seconds, the fuel burns and produces a constant upwards force on the rocket. Before 5 seconds, the fuel is producing a constant upward force. So since there is a constant upwards force, the firework rocket is vertically upwards, fired vertically upwards. The fuel burns and produces a constant upwards force. So when a forward force is produced, an increase in acceleration, there will be an increase in acceleration, which increases because the resultant force increases. So before 5 seconds, the resultant force increases. So somewhere, where is it? The fuel burns and produces a constant upwards force. So here it means F resultant increases, which means the acceleration increases, because remember the acceleration is directly proportional to the resultant force. So before 5 seconds, the resultant force increases. So it means the acceleration increases. So the answer is going to be C. Trolley X moving along a horizontal frictionless track like the stationary trolley Y, the two trolleys become attached to move together. So they become attached to move together, meaning they move with a common velocity. Of course, it means kinetic energy cannot be conserved. When two bodies stick together, the relative speed of approach is not the same as the relative speed of separation. In fact, the relative speed of separation will be zero when they stick together. So which statement about this interaction is correct? Some of the kinetic energy of the trolley X is changed to momentum in the collision. Kinetic energy cannot be changed to momentum of the collision. Some of the momentum of trolley X is changed to kinetic energy. That is not possible. Trolley X loses some of the momentum as heat in the collision. Momentum cannot be lost as heat. It's energy which is lost as heat. Trolley X shares its momentum with trolley Y. That is very true. Trolley X shares its momentum with trolley Y. That is, momentum is conserved, but some of its kinetic energy is lost. Kinetic energy is lost because they stick together, so the answer is going to be D. Momentum is conserved, but kinetic energy is not. An astronaut throws a stone with a horizontal velocity near to the moon's surface. Which law describes the horizontal and vertical forces acting on the stone after release? Which law describes the horizontal and vertical forces acting on the stone after release? So if it is with a horizontal velocity near to the moon's surface, the only force acting here is going to be equal to the weight. The force is equal to the weight, and the weight acts vertically. It acts in the vertical and is constant. So the force is the weight, which is vertical. The weight is vertical, and the weight is constant. The weight of that object will be constant. So which law describes the horizontal and vertical forces acting on the stone after release? So if they have not talked about air resistance, but the moon has almost no atmosphere. So first of all, the horizontal force is zero. There is no horizontal force in the horizontal because the moon has no atmosphere. Horizontal force is zero. So there's no air resistance. So we ignore this one. There's no force acting in the horizontal, even if the object is thrown horizontally. That is horizontal projection. If the object is thrown horizontal, it will fall like that. Reason: the only force acting is in the vertical. The force in the horizontal is zero. The force in the vertical is the weight. So of course the weight of the body remains constant if there is no, because the force due to gravity is the force acting on the body. So the weight remains constant. So the answer is automatically going to be C. Reason: there is no force acting in the horizontal, but there is a weight which is constant. The vertical force is constant. Newton's third law. Newton's third law of motion is often summarized as every action force has an equal and opposite reaction. A book rests on a table. If the weight of the book is the action force, what is the reaction force? So we have a book resting on the table. The weight is the action force. That is, the pull of the earth on the book is the action force. Then the book should be pulling away from the earth. That should be the reaction force. The pull of the book on the earth is the reaction. So the answer is A. The weight is the pull of the earth on the book. The reaction should be the pull of the book on the earth. So the answer is going to be B. This weight is the pull of the earth on the book. The weight is equal to the pull of the earth on the book. So the reaction should be the pull of the book on the earth. Equal but opposite. So the answer is A. A rainy drop falls vertically from rest in air. So since it is falling in air, we expect terminal velocity to be reached. The variation with the time of the speed of the raindrop is shown on the graph. Which statement about the raindrop which statement about the raindrop is correct? So we notice that at x, here the gradient is decreasing, gradient is still decreasing. At z, the gradient is 0. So the acceleration is 0 at z. It is decreasing at x. So at point x, the raindrop has an acceleration of 9.81 meters per second. That is not true because it was already decreasing, so this is not true. At z, the force on the raindrop due to air resistance has reached its maximum value, and so the acceleration of the raindrop has also reached its maximum value. At z, acceleration at z is 0 because it's a horizontal line, so this is also not true. At point z, the force due to air resistance is equal and opposite to the weight of the raindrop, so the speed of the raindrop is 0. At z, the speed is not 0, so this statement is also not correct because at z, the speed is constant. So the answer is going to be D. The resultant force on the raindrop at point Y is less than the resultant force on the raindrop at point X, which is true. The acceleration at X here is greater than the acceleration at Y because the resultant force at X is greater than the resultant force at Y. So the answer is going to be D. A body falling in a uniform gravitational field encounters air resistance. The air resistance increases until terminal velocity. Of course, terminal velocity is constant. Which factor does not affect its terminal velocity? Which factor does not affect its terminal velocity? So terminal velocity, of course, depends on, we know that when a body is falling, at terminal, we know that the weight is vertically downwards because the body is falling, the air resistance is upwards. So the weight down at terminal velocity, the weight downwards is going to be equal to up thrust plus the air resistance or the drag force. So of course the up thrust will depend on the density of the air because up thrust is equal to cross-sectional area times difference, cross-sectional area times difference in pressure. Up thrust is equal to cross-sectional area density times g times difference in the height of the object, or height of the at the top and the bottom of the object. So which factor does not affect the terminal velocity? So the density of the air, this one affects. The height from which the body falls. So this one does not affect. The mass of the body, of course, the mass affects the weight. So that one affects terminal velocity. The shape of the body, the shape affects the drag force or air resistance. So this affects. The height from which the body falls does not affect because this difference in height is the difference between the top of the object and the bottom. This is what I'm calling delta H, not the height through which the object has fallen. So the height from which the body falls does not affect its terminal velocity. Which of the following is a statement of the principle of conservation of momentum? We know that for an isolated system, total momentum is always constant. So the answer is automatically C without wasting time. For an isolated system, total momentum is always constant. The moving object strikes a stationary object. So this one has 0 initial velocity. The collision is inelastic. That means momentum is conserved but not kinetic energy. The object moves off together. So they have the same common velocity after collision. Which row shows the possible values of total momentum and total kinetic energy for the system before and after collision? Let's begin with total kinetic energy before and after. It should be the same. It should not be the same because the collision is inelastic. So if it is the same, that one is not correct. So we ignore what D, because D is showing same kinetic energy. But then, if the collision is inelastic, it means kinetic energy before collision is most likely going to be higher than kinetic energy after collision, because there is no possibility of the velocity of the common object or the combined object to be higher than the velocity of an object which was moving alone. Yet the one which was moving alone is the one which gave some momentum to the one which was stationary. So it means total kinetic energy before could be higher than total kinetic energy after, because kinetic energy is going to be lost. So it means we shall ignore B also, because kinetic energy before should be greater than kinetic energy after. So we ignore B. So we have ignored B and D. Okay, so we have to choose between A and we have to choose between A and C. So total momentum before collision should be the same as total momentum after collision. Momentum must be conserved. So total momentum before collision should be equal to total momentum after collision, because whether the collision is elastic or inelastic, momentum must be conserved. So it means we ignore A because the momentum is not the same. So the answer is going to be C. A wooden block is freely supported on brackets at a height of 4 meters above the ground as shown. A bullet of mass 5 grams is shot vertically upwards into the wooden block of mass 95 grams. It embeds itself in the block. The impact causes the block to rise above its supporting brackets. The bullet hits the block with a velocity 200 meters per second. How far above the ground will the block be at the maximum height of its path? So let's say it moves when it is hit. Let's say it moves to this position here with the bullet in it. So the bullet is in it. So it has moved through a height h. So let me call this one small h. So the question is how far above the ground? So we need the whole value of this height here. So this will be 4 plus h. That is how far it has gone, because it is 4 meters above the ground, then plus h. Okay, so first of all, we are going to conserve momentum and find the speed with which the system moves initially. We're going to conserve momentum to find the speed with which the system moves after collision. So before collision, it is only the bullet moving. So its momentum is going to be 5g times its speed, which is 200 before collision. It's the bullet which is moving. The other one has zero momentum because it was at rest. After collision, they stick together. So their mass becomes 5 plus 95, which is 100 grams. Then times the speed, they move with the common speed, which I'm going to call u. Of course, grams cancels out. That's why I didn't change the units. So if I make u the subject, I just find u, the speed with which they move after collision. U is going to be 1000 divided by 100, which is 10 meters per second. So the system moves with that speed. But reaches the highest point, that means final velocity becomes 0. At the highest point, because it's moving against gravity, at the highest point, velocity becomes 0. So if air resistance is negligible, then I'll use v squared equals to u squared plus 2as. So this will be 0 squared equals to 10 squared minus, because it's moving against gravity, 2 times 9.81, then times small h. So what is small h? Small h will be 100, 10 squared, which is 100, divided by 2 times 9.81, which gives us 5.1. So small h is 5.1 meters. So the distance we want, which is 4 plus h, is going to be 4 plus 5.1, which is going to be 9.1. So the answer is C. Alternatively, we would also use, to find small h, we would also use a loss. in kinetic energy is equal to the gain in potential energy. So those in kinetic energy is a half times m v squared is going to be equal to m gh. So m cancels. So a half times the initial velocity, which is 10 squared, is equal to 9.81 times h. Still, this gives you h as 5.1 meters. Then you add it to 4 to get 4 plus h, which is 9.1. One of the equations of uniformly accelerated motion is shown here. Apparatus is arranged to record the time t taken for a marble to fall between two light gates connected to timers. The marble touches the stop before it is released. The vertical distance s between the light gates is measured. Okay. Which graph does not show a correct relationship when light gate 2 moves up to light gate 1, which is fixed? Which graph does not show a correct relationship when light gate 2 moves up to light gate 1? Light gate 2 moves up to light gate 1, it means S decreases. S decreases. If S decreases, then what happens to T? If S decreases, since it is falling, initial velocity is equal to 0. So S is going to be equal to a half at squared. The acceleration is constant. Initial velocity is 0 because it's falling from rest. So as S decreases, what happens to T? As S decreases, T also decreases. But now let's look at the graph. So S, if I plot S, this is a graph of S against T, and we see that S is directly proportional to T squared. So this is going to be curved. So this is correct. This one shows the relationship. Then for this one, it is S. If I plot S over T, I think S over T is directly proportional to T if you modify this equation. So this is also going to be correct. This is a correct relationship since S is equal to a half at T squared, then S divided by T is equal to a half at T. So it means S over T should be directly proportional to T, which is a straight line. So that is correct. Then U against T is a horizontal line along the x-axis. Let me begin with the D. D is correct because acceleration is constant. Since acceleration against time is constant because the body is falling, and if we assume air resistance is negligible, then the acceleration is directly proportional to T. I mean, the acceleration is constant, so this is automatically correct. The acceleration is 9.81. So this one is not going to be a correct relationship because it's showing that as S decreases, as S moves towards as S becomes smaller, it is showing that initial velocity remains 0 throughout, but there is no relationship between U and T. U is not depending on T, so this one means this is not going to be a correct representation, because the question was which graph does not show a correct relationship when light gate 2 moves up to light gate 1, which is fixed. So the relationship between U and time, U will not remain 0 throughout when time changes. So that means the answer is going to be C. C is not correct. A stone is dropped from a height of 20 meters above water. The graph shows the variation in time of the velocity of the stone. Which statement describes the approximate position of the stone 4 seconds after it is dropped? Approximate position of the stone 4 seconds after it is dropped. I think we have answered a similar question. So let's see the distance for it to reach the water. So S to reach the water surface. So the distance to reach the water surface, S to reach the water surface, distance, this is a triangle. S to reach the water surface, distance is the area under the graph. So this is going to be a half times the base, which is 2, times the height, which is 20. The distance to reach the water surface is going to be 20 meters. Then S, when it is in water, so here at this point here, it has touched the water. So here, hits the water. So it rapidly decelerates. So S when it is in water, S in water is going to again be area under this part here, which is 4 minus 2, that is 2, times 5 minus 0, which is 5. So the distance in water is 10 meters. So it means here it moves in 10 meters in water, so it is 10 meters below the water. So the answer here is going to be B. It is at a distance of 10 meters below the surface of the water, because it hits the water after moving 20 meters, but when in water, the distance it moves is 10 meters, so it is 10 meters below the surface of water. The water surface in a deep well is 78 meters below the top of the well. A person at the top of the well drops a stone down the well. So initial velocity is 0 because it is dropped. Air resistance is negligible, meaning the acceleration is constant. The speed of sound in the air is 330 meters per second. What is the time interval between the person dropping the stone and hearing it hit the water? So let's first of all find the time to fall, the time it takes to fall to the bottom of the water. So time falling. Time falling, of course, I'll use S equals to UT plus a half AT squared. So it falls a distance of 78 meters. Initial velocity is 0, so this part will be 0, so this is equal to a half times the acceleration, which is 9.81, then times t squared. So what is t? The time of falling is going to be 78 times 2 divided by 9.81. Then I find the square root of the answer. So that is 3.99. 3.99 seconds. Time it takes to fall to the bottom. Then, of course, the sound reaches, it falls to the bottom, and then the sound must return. So, although the distance remains the same, 78, but the speed is changing. So, time for sound to reach the person. T for sound to reach the person. So time is going to be distance over, because the speed is constant, it's going to be the distance divided by the speed. The distance is 78, but the speed is 330. So 78 divided by 330. So that is 0.236 or 0.237. So this is 0.237 seconds. So now we want the total time. So total time is going to be 3.99 plus 0.237. No, it is 236. Because it is 36 recurring, 36, 36, 36. So it is 0.236 plus 3.99. So I get 4.22. So the total time is 4.22. So the answer is D. A golf ball is hit by a club. The graph shows the variation with time of the force exerted on the ball by the club. Which quantity for the time of contact cannot be found from the graph? Which quantity? So first of all, force against time, we know that force is equal to the rate of change of momentum. So the average force on the ball, this one we can find the average force from the ball, from the graph. Then the change in momentum, force is the rate of change of momentum, we can find from the graph. The contact time between the ball and the club, we can find this from the graph, the contact time at that point. Then the maximum acceleration of the ball, we cannot find this from the graph. We can't find acceleration from the graph, maximum acceleration. We can find the acceleration, but not the maximum acceleration from the graph, because the resultant force is equal to the rate of change of momentum. This gives us the constant acceleration, but this is not constant. This force is we cannot find the maximum resultant force from the graph, so we cannot find the maximum acceleration of the ball from the graph. So that is not very possible. A glider of mass 1,500 kilograms is launched from rest on a straight and level track catapult. The graph shows the variation with time of the resultant force. What is the speed of the glider when the resultant force acting on it reaches 0? So we know that force is equal to the rate of change of momentum, which is mass into change in velocity divided by time. So the mass is, let's say, what is the speed of the glider when the resultant force is 0? So when the resultant force is 0, it means when the resultant force is equal to the rate of change of momentum, which means the change in momentum is going to be equal to force times time. And of course, this is going to be the area under the graph, the area, which is going to be the area. So force times time is going to be, the change in momentum is going to be, if I have a graph of force against time, so the area under the graph is going to be the change in momentum. Okay, so it means the change in momentum is going to be equal to a half, because the area here is a triangle, so it is a half times 10,000, then times 40. So I think this is 20,000, no, 200,000 Newton seconds. So that is going to be the change in momentum. That is 200,000 Newton seconds. So change in momentum is going to be the area under the graph. For a graph of force against time, change in momentum is the area under the graph, because it can't. This only applies if this is constant. If it was a horizontal line like this, then the change in momentum will be force times time. But since it is the f is not is varying with the time, then it is going to be the average force with the time, or the change in or simply the area under the graph. But then we also know that change in momentum is equal to mass times change in velocity. So the change in momentum, which is 200,000, is going to be the mass, which is 1,500, then times change in velocity, which is the final velocity minus 0, because initial velocity was 0. So we get V as 200,000 divided by 1,500. Okay. So this is going to be 200,000. So just the answer divided by 1,500, which means V is going to be 133.3 meters per second. So our answer is going to be A. The answer there will be A. Which statement about a ball that strikes a tennis racket and rebounds is always correct? Which statement about the ball that strikes a tennis racket and rebounds is always correct? Okay. So if it rebounds, it means momentum is always conserved. So let's check momentum is always conserved. Which statement about a ball is just a ball? Okay, so if it is just a ball, it means the momentum of the ball is not conserved. But if we consider the ball and the racket, then total momentum of both will be conserved. But since it is just about a ball, its momentum is not conserved. So total momentum is not conserved. Total momentum of the system is the ball and the racket. This one is always conserved. Total momentum of the ball alone is not conserved. Total kinetic energy of the ball is not this is not correct. If we say total kinetic energy of the ball is conserved, that is not correct, because if the ball hits the racket, then some energy could be lost or some energy is gained from the racket. So the total kinetic energy before and after may not be the same. So total kinetic energy is not conserved. Kinetic energy of the system is conserved. This may not be conserved because even the racket may warm up. So it is only the total momentum of the system. The system is the system of the ball and the racket, not the ball alone. That's why I said total momentum of the ball is conserved. This is not correct. Total momentum of the ball alone is not conserved because it changes. But total momentum of the system, which is the ball and the racket, is conserved. If the system is isolated, total momentum is always conserved, and the system comprises of two objects, the ball and the racket. A boy throws a ball vertically upwards. It rises to maximum height where it momentarily comes to rest, so that means velocity there is 0, and falls back to his hand, which law gives the acceleration of the ball at various stages in its motion. Take vertically upwards as positive, ignore air resistance. If air resistance is ignored, acceleration is always going to be constant in magnitude. But when it is going up, acceleration upwards is going to be negative, and since initial motion is negative, acceleration will remain negative throughout. Since initial motion is negative, acceleration will remain negative throughout. If we sketch a graph of velocity against time, the ball is thrown vertically upwards. That means it has an initial velocity. So because it is falling vertically, it is thrown vertically upwards, it slows down as it goes up to 0 velocity. When it changes direction, velocity increases in the opposite direction. So this line here has a constant gradient, which is negative. So the acceleration remains negative throughout. So the answer is going to be B. Rising, it is negative. At maximum height, it remains negative. Then if it is falling, it remains negative if air resistance is negligible. So the answer is going to be B. There's no point where the acceleration due to gravity will be 0 at maximum height. So the answer is going to be B. It can't be positive because the initial direction is upwards, so the acceleration remains negative. The ball is released from rest above a horizontal surface, it strikes the surface and bounces several times. It bounces several times. The velocity time graph for the first bounces is shown. What is the maximum height of the ball after the first bounce? Okay, so for the first bounce, the height it reaches is this one here. For the second bounce, so here it reaches it. Here it is hitting. Here it hits the surface. At this point, here it hits the surface and bounces. When it bounces, it moves up. Now this one it is moving up. It reaches 0 velocity. That means it has reached the maximum height. Here it is now again. It is now falling back downwards to hit the surface again. Here it is again hitting the surface. So here it hits, and here it hits. Here it is at maximum height, where the velocity becomes 0. So what is the maximum height of the ball after the first bounce? So after the first bounce, this is the area we need here. So the height h is going to be a half times 0.5 minus 0.3, which is 0.2, times 2, which gives us 0.2 meters. So we need the area under this part here because this is the distance it moves to the highest point after the first bounce. So we get the area there, which is 0.2. So the answer is A. takes a time of 25 seconds to reach a constant speed while traveling in a straight line. It takes 25 seconds to reach a constant speed while traveling in a straight line. A graph of speed v against time t is shown. A graph of speed v against time t is shown. So there's a question missing here, and the question missing is which graph shows force against time for the bus? Which graph shows the force against time for the bus? So this is the missing question. So if it reaches constant speed, you know that force is equal to mass times acceleration, which means the force is directly proportional to the acceleration. So when at constant speed, of course, at constant speed, the acceleration is 0. It means the force should go to 0. So here, this point here, at constant speed, here acceleration goes to 0. So F should go to 0. When acceleration tends to 0, F should tend to 0. So the graph should be going to the 0 axis. So we ignore C. We now remain with A, B, and D. So here we have a straight line, which means the acceleration is constant, A is constant, F should also be constant. So we ignore B because B is not showing constant force. We also ignore D because between t equals to 0 to around t equals to 5 or just after 5, the force is not constant. So at this point, because it's a straight line, the acceleration is constant. Remember, the acceleration is equal to the gradient, and the acceleration is directly proportional to the resultant force. So when the acceleration is constant, because the gradient is constant at this point here, it means the force should also be constant. So our answer is going to be A. An object of mass m traveling with speed v has a head-on collision with another object of mass m traveling with speed v in opposite direction. The two objects stick together, that means they move with a common velocity after the collision. What is the total loss of kinetic energy in the collision? Total loss of kinetic energy in the collision. Okay, let's first find, let's use conservation of momentum to find the initial velocity, the final velocity. Initially, total momentum is going to be m times speed v for the first one. It has a head-on collision with another object of mass that moving in the opposite direction. So total momentum will be plus negative m times v. This should be equal to total momentum after collision. Because they stick together, total mass will be twice m, and let the speed after collision be u. Because mv plus minus mv is equal to 0, it means the speed after collision is going to be 0. So that means total kinetic energy after collision, since the speed is 0, total kinetic energy after collision is 0. It means that the system remains at rest. But then, kinetic energy before collision is going to be a half. For the first mass is m times v squared plus a half. For the second mass is m times v squared, which is going to be just m v squared. So this is total energy before collision. So the change or the loss in energy is going to be mv squared minus 0, which is simply mv squared. So the answer is C. Lastly, for this video, two identical spheres x and y approach each other with the speeds shown and undergo a head-on elastic collision. For elastic collision, the relative speed of approach should be equal to the relative speed of separation. So relative speed of approach is equal to 4 minus negative 2, which is equal to 6. It means the relative speed of separation should also be equal to 6 if the collision is elastic. So it means A, we have 2 minus 0, which is 2. So this is out. B, we have 4 minus 2. There is in the same direction. 4 minus 2, which is 2. So this is not elastic. Then we have 4. C, we have 4 minus negative 2 because minus 2 is in the opposite direction. This gives us 6. So the answer is going to be C. Relative speed of separation is 6. So the answer is C. D is 4 to the left and 2 to the right. This also gives us 6, but because it gives us negative 6 anyway, 2, it gives us 6, but this is not going to be correct because it means it's like x retained its speed. It rebounded with the same speed, which practically is not going to be possible for both masses to rebound with the same speeds in the opposite direction. So this is not going to be true. So it can't rebound because x was moving with 4 meters per second. So on rebound, it cannot rebound. I will say can't rebound with a higher or same speed. There must be exchange of speeds. Okay, let part 10 stop here. See you in part 11. Bye bye.